A differential is not a part of a car in this class. It is related to a function. If we have a function, um, we have an input, and then we're going to move the input to another input, and we have a corresponding output here. And then we have a tangent line, pretend that is tangent here. So again, we start with an input, we go to another input that creates an output corresponding to the second input, and this is the output corresponding to the first input. So first input, second input, first output, second output. Okay. Oftentimes, we want to relate those outputs with the straight line, the tangent line instead. Many, many times we want to do that. The distance here across is going to be labeled as delta x or dx, same thing in the horizontal case. In the vertical case, they're going to be different. This distance will be delta y, while the distance up to this point will be dy. So dy, which is going to be labeled as the differential, is the distance using the straight line, which is tangent to the curve. So there's going to be a curve, a function, and so the differential is relative to the function. Now, here we have a right triangle. Okay, so, and this is the situation we have a dy on the right triangle. On the curve, we wouldn't have a right triangle, we would have a curve, and then this is dx. And if you know the slope of this angle, then we know that the slope is going to be dy. I'm going to put parentheses in dy to emphasize this is a quantity divided by dx, a quantity. It's not dy dx, it is the quantity dy. So the differential is going to be a quantity this much over this much, rise over run, and that gives us the slope. The other way to think about it is that dy, if we multiply both sides by dx, we end up with m dx. Yep. But these are quantities. We're not thinking of dy dx. Yeah, dy dx, let me just make a quick note about this. Dy dx is not really dy dx. Dy, on the other hand, dx is really an operator applied to y. So this is so as an operator, this is the name of the operator, dx, cannot be broken up. It's a name. It cannot be split up into parts or pieces. It's not actually a division. It comes from a division of the corresponding deltas after we take the limit. So be aware of that. That's not the case. Be very careful when we're multiplying. So as quantities, because I started the picture using dy as the rise and dx as the run on this picture, so they're quantities, we can multiply both sides. So that's how we define dy. The differential on y is the slope at that point multiplied by how far we go out, and that gives us dy. That's the definition of differential of y relative to x. So this is, all of this is Calc 1. How we're going to do that in Calc 2? So we're going to put a division here. Okay, so in Calc 2, we're going to have a sheet that is going to come down. So pretend that is a rectangular. Well, I shouldn't say that it is rectangular. The domain is rectangular. That is what I'm trying to say. So pretend this is rectangular. So this is a bad angle. This should have been 90 degrees from this line to this line. And then this comes this way until it goes here, there. So the bottom is rectangular. I should have probably started with the bottom and then draw the top from there. So again, pretend this is a distance, and then this is, yeah, I should probably start with a new picture. So again, the bottom is rectangular. So this is my domain. And on top of that, there's going to be a plane. Yeah, this is going to be way better, this picture, I think. All right. And then we're going to do a parallel to this and a parallel to that. It should match perfectly. This should go up to here. There we go. So this is the sheet for which we're going to define the differential. This is the plane, as opposed to, so as opposed to a straight line in Calc 1. So this straight line, all of a sudden has become this plane, which is attached to a surface. I don't want to draw the surface because it's going to be even more complicated. So pretend this is a dx, and down that way, we're going to have dy. dy. And the question is, okay, what is dz? So we're assuming dx and dy are independent of one another. So what is dz? Yeah, that's the question. What is dz? Equals what? Now, we're going to assume there's a slope here in the x direction. We're going to label that as m sub x, and a slope on the y direction. So I'm kind of turning things around a little bit, because usually x is towards us and then y is to the right. So in this case, we turn it 90 degrees, so x is to the right and y is away from us. And the question is, how do we get to this point if we only know this, that, and that slope and that slope? We do not know this slope. By the way, this slope is different than those two. In one of the previous videos, I had this kind of picture, or this board and a coin, and if I let it slide, it will slide down this, which means that it's not, that the slope this way is not the same as the slope which is diagonal there. If we put a pen to stop it from going in the diagonal direction, then of course we're going to go in this direction, which means that this is not the same as that. Okay, so how do we get to this height using dx, dy, and their corresponding slopes, which are not the slope as this one? Well, if you go this way, this distance up to here, this distance will be m sub x dx. It is dy, actually. Yep. Well, no. I shouldn't say dy. I was sorry. I was confusing. When I said dy, that was wrong, because I was confusing the two-dimensional, the x and the y, with here the x and the y are independent, so dy is not part of dx. They're not part of dx. Okay, so m sub x dx, that's this distance. Now pretend you got this much, because this is a rectangle. So this distance here is the same as this distance, which is the same as this distance, which is dy, and this slope is the same as this slope, which is m sub y. So this portion from here to here is m sub x dx, while this portion here that is missing to get to the top, so we're climbing up here, go across, climb up again, that's going to be m sub y dy. M sub y dy. It's the same picture as this triangle, except that it's going sideways. So this is a right. And the reason is because those are vertical, perfectly vertical. This one, that one, and that one is vertical. This one, well, there's no vertical because that is the starting point. And we can do the same thing the other way. We can go across and up. So this height here is m sub y dy. And then if you go across horizontally, which doesn't necessarily match with that. That is not necessarily true. In this picture, it almost seems like this distance is the same as that, but that is pure coincidence. Then we have to climb up this distance. Either way you do it, whether you go this direction or this direction, I hope it is clear that dz, which is the distance from the bottom to the top, is m sub x dx plus m sub y dy. And that is the formula for the differential on z when you have x and y as independent variables. Most people label that as f sub x because we're really talking about a surface, and that is f sub y. And that is correct also. That's absolutely correct. Let's do an example. Example 1. Okay, so one thing we could do with differentials is that we can approximate outputs of a function. See, if the differentials are small enough, if these numbers are small enough, the difference between the real output, which is this one, and the output corresponding or using differentials is very tiny. Many, many times this is very, very small, negligible, very, very tiny. Tons of computer applications use differentials, and they perform just as good as the function themselves, and they save a lot of time by doing that, because it's easier to multiply than to do other functions that are more complicated than just multiplying. Yeah, so there is the example. The example consists in, there's a couple different ways to state the example, but okay, so find differential of z equals the square root of x squared plus 2y at the point 5, 12. So that's the input. And use this information to approximate the output of z at 5.3 comma 11.9. Okay, so this is a standard kind of problem to do, dealing with differentials and approximations. I'm kind of mixing the two, the differentials and the approximation, in the same problem. So the differential is m sub x dx plus m sub y dy. That's as simple as that. That is from the previous page where we had the picture, this picture, there we go. So you climb this way and you get m dx. You climb this way, you get m di, add them together, and it gives you the distance, the vertical distance from this corner to this corner vertically. Or you can go the other way. So you can start with this, add that, if you go in the other direction. But we gotta be specific to this function. So first we find the partial of the function. Even though I did not label it as f, let me modify this. This is f of x, y. Now, I'm gonna label it f, and we can find the derivative. So the derivative of the square root in general is 1 over 2 times the same square root. There we go. So that is the derivative of the square root. And the reason is because the derivative of a quantity to the 1/2 is 1/2 times the same quantity to the -1/2 So the 1/2 again is showing up as a root, and negative means as a denominator. But then because of the chain rule, we got to multiply by the derivative of the radicand. So the derivative of x squared plus 2y with respect to x is 2x. So the two simplify, and we end up with x over square root of x squared plus 2y. By the way, we never found the output at that point. We should probably do that. That's okay. We're going to find it right now as we find the slope. Okay, so f sub x is the generic formula. If we plug in the numbers 5 and 12 into here, then we end up with the slope. So x is 5, y is 12. 5 over square root of 5 squared plus 2 times 12. So that is 24 plus 25 is 49. Square root of 49 is 7. There. So m sub x is 5 over 7. Oh, which means since this root is the same as this root, it means that the point at which we are doing this is 5, 12, 7. The z value is 7. Yeah. So remember that. F sub y is going to be, again, so we're taking the derivative of this quantity with respect to y. The derivative of our root is 1 over 2 times the root. By the chain rule, we have to multiply by the derivative of x squared plus 2y with respect to y, which is just the 2, not 2y, because we don't have y squared, we have 2y. The derivative of x squared with respect to y is 0. The derivative of 2y with respect to y is 2. The 2 simplify, and we simply end up with 1 over the square root. So the slope in the y direction at this one point will be 1 over 7. Okay. So the differential with respect to z will be 5/7 multiplied with whatever dx is plus 1/7 multiplied with dy. See, this is what's going on. We have an inclined plane, which may be more steep in one direction than the other. So this picture suggests that this slope is more gentle than this one. And by the way, this is going to be even more steep than this one. But this is more gentle than this because of the distance, as this takes longer to get to this point, while this takes shorter to get to a similar point in altitude. And so it looks like this is steeper than that. All right. And so to get to this point, this distance is contributing, as we move in this direction, that contributes more to going up higher. And that's what this tells us. The contribution in the dx direction, not necessarily much in this picture, but the contribution of the dx going in the dx direction provides more altitude than going into the dy direction, in the y direction. That's what this is telling us. And by the way, those two numbers don't have to add up to 1. They add up to whatever. And one number may be negative, the other one may be positive if the plane is going in different directions. So that is what's going on here. There's a differential. That is half of the problem. The problem is asking, find differential. We found it at that point. Yep. So now we want to approximate this output. Pretend you don't have a square root button. Pretend the square root button is broken on a calculator. And you want to find the square root of 5.3 squared plus twice that much. I'm just going to figure out very quickly. 5.3 squared equals 2809. Okay, so f of 5.3 comma 11.9 is equal to the square root of 5.3 squared plus 2 times 11.9. So that is the square root of 2809. 2809 plus 2223.8, and if we add those together, we get 0.89. 3 and 8 is 11, carry 1, 2 and 2 is 4, and 1 is 5. So let's say you wanted to find the square root of 51.89 using this function and using differentials at this point. Okay, we know that the output at this point is 7. Let me rewrite that again. So we know f of 5 comma 12 is the square root of 5 squared plus 2 times 7. Whoops, I'm sorry, 2 times 12. 12. 2 times 12. So that is square root of 25 plus 24, no, square root of 49, which is exactly 7. So the output here is 7. But we want to deviate from this point a little bit. We want to move 3.3 units towards us and 1 unit away from us. You know, if this was 5, if we were on the space and this was 511 somewhere, rather 512, we want to go 3 units this way and 0.1 unit this way, and we want to know how the output will change. The output here is 7. So what is the new output? We don't know. We want to find out. That's where the differential comes into play. So in this case, plug in the correct dx and the dys. We're going to find that dz, the change as we go from 512 to 5.311.9 will be 5/7. The amount we change on the x value. Well, if we're going from 5 to 5.3, we changed 0.3. So I'm going to put that as a decimal, rather as a fraction. 0.3 is 3/10. So that came from going from 5 to 5.3. Plus, the contribution in the y direction is 1/7 of whatever the change is. The change is -1, -0.1, because we are going down from 12 down to 11.9. So -1/10. All right, that's going to be 15 over 70. Multiply that out, minus 1 over 70. That is 14 over 70. Boy, that's working out without even realizing it. So 7th out, that's 2. 7th out is 10. So that is 2/10 is 1/5. Oh, that's 0.2. 0.2. Yep. So it turns out that the square root of 51.89 is not 0.2, obviously. It is going to be off the 7 by 0.2. So the approximation, we can approximate f of 5.3 comma 11.9, which is really the square root of 51.89, and we claim that that is going to be off the 7 by about this much, 7.2. So that is the approximation. Notice that we put approximation. But my calculator does work. I'm curious to know how far off we are from the actual answer. But in actuality, the square root of 51.89 is, well, I'm going to obtain an approximation anyway, but it's a decimal, a closer decimal approximation, 51.89. Okay, so 51.89 7.89. I'm using my calculator. And then square rooted 7.2. Oh, this is sweet. So this approximation, 7.2034713. And the reason why I say it's an approximation is because the calculator has many more decimals after, but of course we're not writing all of the decimals because we don't have them. But this is a more precise approximation than this one. But notice that how close we were. We were 3 or 4 thousandths of a unit. That's really, really small. This approximation without using square root key is very, very good. So that's how we approximate outputs. Remember to start with the 7. Remember what those mean. Those are actual contributions of each one of the directions. And that's how we obtain the output. Actually, we lost as we went back, but that's okay. It worked out really, really, really well. So with this, we finished this video.